What's up, everybody? It's Dan from SageMathTutoring.com. I am here with a video where I'm going to help a student get through a test review sheet for physics. Okay, now this is the physics section that has to do with energy, um, and actually it's quite a comprehensive overview of various concepts. There is the concept of work is involved, the concept of gravitational potential energy, kinetic energy, elastic potential energy, and some other notes that I made over here. So these notes feature the various formulas and some pieces of information that are definitely going to become helpful when it comes to solving these problems. So I actually say that we dive right in to solving the problems now. So let's take a look at the first one. So the first one says, a small block with a mass of 250 grams starts from rest at the top, that's right here, of an apparatus shown above. It then slides down without friction down the incline around the loop, so it goes like that, and then onto the final level section on the right. The maximum height of the incline is 80 centimeters, and the radius of the loop is 15 centimeters. So my first instinct is saying that we should probably label that, right? We should probably label that. So I'm going to do a little label here that says that that is 80 centimeters. And this is 15 centimeters. I'm just going to write 15 there. And looking at lowercase letter a, find the initial potential energy of the block. So the block's up here, and it has a certain amount of potential energy. Now, the block is not moving right away, but it's suspended up in the air. It's on an apparatus, but it's up kind of high. There's a height going on there, and that height is 80 centimeters. So this section over here on my notes serves as a reminder that if you're sort of dealing with height in general, you might want to start thinking in terms of gravitational potential energy and start working with some of these equations and this information over here. Now, when the teacher asks for the initial potential energy of the block, well, we're going to look at gravitational potential energy. And according to this formula, right out the gate, gravitational potential energy equals the mass times gravity times the height. So that's actually going to be pretty easy if you think about it, because we definitely have the mass already. The mass is 250 grams. We could convert that to kilograms soon, but we have the mass. We also know what gravity is. That's 9.8 meters per second squared. That's actually written right here. And as a reminder, the unit of measurement for mass that we're going to want to use is kilograms. And then we also have the height. I mean, the height is in centimeters, right? So we basically have all the information we need. Now, it is also worth noting that when you're dealing with length, even including like height, that kind of a measurement, you're going to want to deal with meters, okay, meters. So there is already, I can see some unit conversion that might need to take place. Now, my view is, we could do that very soon, but let's be very clear that the equation we're going to use, once again, is this one, where it's gravitational potential energy equals the mass times gravity times the height. And I'm a big fan of empty parentheses, so that's going to equal the mass over here times gravity times the height. Now, gravity we already know is going to be 9.8, and that's meters per second squared, but I'm just going to write 9.8 here. Just understand that if I wanted to, I could write meters per second squared. With regards to the height, which is over here, let's actually take care of that now. Now, we know that the height is 80 centimeters, but in reality, if we did a unit conversion, we could have 80 centimeters, and then we could set up the fact that there are 100 centimeters in 1 meter, and therefore, with that unit conversion, you could cancel not the number, but the word centimeters, right? And then we're left with just the unit of measurement meters, and that's going to be 80 over 100. which is 0.8 if you were to do that as a decimal. So that's going to be the height, which I'll put over here. And now we are looking at the mass, which belongs over here. Now, they said that the mass is 250 grams, but, let's do a little unit conversion there as well, because the unit for mass that we want to work with is kilograms. So let's write 250 grams. And we know that there are 1,000 grams in 1 kilogram. So therefore, we can cancel out the letter G, and that's going to be 250 times 1 over 1,000. So you just multiply straight across. So 250 over 1,000 is 0.25. 0.25. So that's really all there is to that one, because at this point we will just multiply that. All right, we're going to multiply 0.25 times 9.8 times 0.8, and that would be 1.96. And that would be joules. That would be joules. If the teacher's looking for that, you could write that J there. Okay, so the next question is find the velocity of the block at the bottom of the loop. So I'm sort of drawn to this part once again of the notes where if height is involved, you're going to want to look at the gravitational potential energy stuff. If you're dealing with how fast something is moving, like velocity, you're going to want to deal with kinetic energy. And just for the record, if you're dealing with a compression of a spring or something like that, you're going to want to deal with this elastic potential energy. Now, elastic potential energy is down here. I've got some information there. Kinetic energy is over here, and gravitational potential energy is over here. So, yeah, this is actually a really good resource, I have to be honest. You might want to screenshot it and save it, on your computer. But nonetheless, we have find the velocity of the block at the bottom of the loop. So this thing goes down, 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 and then right around here, it's going a certain speed. And the question is, well, how fast is it moving there? Well, once again, when we're asking how fast, we're going to want to look at kinetic energy. Ultimately, what we're asking is what is the kinetic energy in that moment? Now, it is worth noting that since energy is a closed system, gravitational potential energy will equal the kinetic energy, okay? Now that's something that I'm going to leave that to the teacher to explain that. Also, you could always check out various YouTube videos to just figure out, how is it the case that potential energy always equals the kinetic energy? But that is the case, okay? That is the case. So just take my word for it. Gravitational potential energy is going to equal the kinetic energy due to the closed system aspect of it. And we already know the gravitational potential energy here. We already figured that out. It's 1.96. So it is sort of on us to remember that, the 1.96 is going to be equal to the gravitational potential energy. That's what we just discovered, in the last problem. But that's also going to be equal to the kinetic energy, okay? And once again, that's written right here. For my student at home, I would say write that down. That you should have that written somewhere. I put an asterisk there to relate it to this situation, okay? So 1.96 is going to be equal to the kinetic energy. And we know that the kinetic energy is 1/2 the mass times velocity squared. So I'm just going to write that over here. I'm going to rewrite the situation as 1.96 equals 1/2 the mass times velocity squared. Okay, so let's blow this up a little bit and really take a look exactly at what's happening here. So we know that the mass, we already figured that out before here, that's 0.25, right? So we know that we could definitely substitute 0.25 in for this m. And that would certainly bring us far enough along in this equation to just solve for v at that point, okay? Now, what I'm about to say might be a little bit of a departure from what you've learned in algebra, but when it comes to a lot of these problems, even before you've substituted all the values in, you might want to get clear about, okay, well, which variable am I solving for? In this case, it's definitely the velocity, right? It's definitely the velocity. So even before I substitute 0.25 in for m, you might want to actually treat this as a literal equation and solve for v. That way, when you plug stuff into your calculator, you only have to do like one calculation in your calculator, especially if you're using a graphing calculator or Desmos or something. You can actually save yourself a lot of trouble. Now, when we manipulate that equation to solve for v, what we would quickly get is, I'll actually extend this, we'll go over here with it. What we would quickly get is that v would equal the square root of 2 times 196, 1.96 rather, all over the mass, okay? Now, for my student at home, if you have to confirm that, just, multiply both sides by 2 to get rid of the 1/2, divide by the m to get the m down below, to get rid of this m, and then take the square root to get v by itself. So if my student at home actually attempted to get v by itself, it would most definitely become this. Now, let's be very clear. The m we already have, the mass we already have, it's 0.25. So I'm actually going to go ahead and write that, 0.25. Now, hopefully, my student at home can see that the benefit of doing this, if you could avoid getting confused and just remember how to isolate, v, you're going to have to isolate v squared first and then take the square root at the final moment of it. If you could get this far, it actually makes your life easier because now you can just plug all this in, starting with the square root, take the square root of this, all right? Now, I'm a big fan of Desmos, actually. I would suggest any student get the Desmos app because that calculator is fantastically intuitive. So you'd literally write a square root symbol first, and then you could write this thing with little parentheses around it, etc. But one way or the other, once you plug all this information in to your calculator, you would get, at the end of it, v equals 3.96, and that would be meters per second, because that's the unit of measurement for velocity. Okay, so that is that one. I'm going to leave that off to the side. So for my student at home, just know that that is the answer to lowercase letter b. All right, looking at the next one, we have problem number 2. Problem number 2, I'll get rid of all this actually for now. A 0.8 kilogram block is attached to the end of a spring whose spring constant is 85 newtons per meter. The block is placed on a frictionless tabletop given the initial displacement of 3.5 centimeters and then released. What kind of energy did the block spring system initially have? So that would be elastic potential energy, because when they say, what type of energy did the block spring system initially have, that means before you released it. So you had a spring that was either stretched or compressed or whatever, and the block was just kind of hanging out there before it was released. And in that moment, even intuitively speaking, you can understand that it has potential energy, right? It's not moving yet, but it has potential energy. And since we're dealing with a block spring system just in general, that means we definitely want to be looking at the elastic potential energy, all right? So the answer to that one is pretty straightforward. It's almost like a vocab question, to be honest. So that would be elastic potential energy. I'm just going to write EPE for that one. And then they're asking, find the magnitude of this energy. Now, that's just fancy language for find the actual elastic potential energy. And that's all they want to know. So in order to find that, well, down here we can see that elastic potential energy would be 1/2. Now K is the spring constant, okay, and that is given in the problem. And X is the displacement, okay, how much the spring is compressed sort of distance-wise, okay, how much it's compressed. And that's given in the problem too. Now, I'm going to be a little bit more organized because also I can already have the sense that the teacher probably would prefer if we wrote down the cast of characters before we started solving the problem. So I'm going to do a little divider here. And the truth of the matter is we definitely need K, and they give that to us. K is 85. Okay. Now we do not have to do a unit conversion there because we're already given the proper unit here. It is newtons per meters, okay? So we could just leave that alone. We don't have to convert it. But we will need the displacement, and the displacement x is going to be this. So that's going to be an initial displacement of 3.5 centimeters. But we need to understand that the unit of measurement for displacement that we want to work with is meters, so we will have to convert that to meters, and that's going to be a result of dividing 3.5 by 100, which moves decimal place over twice to the left. So that's going to be this, okay? 0.035 meters. Now, if you have any question about how I did that unit conversion, it's actually exactly the same process here. I could have put 3.5 centimeters here with 100 centimeters down below. I could have canceled it, and it would have ended up being 3.5 over 100, which is also known as 3.5 divided by 100, which means you move that twice to the left, okay? Now, when in doubt, if you don't like doing this in your head, you could always just go and do something like this and do the unit conversion. But regardless, we now have the information that we need to flesh out this equation down here. So in order to find the magnitude, in other words, in order to find the elastic potential energy, we could set that equal to 1/2 K times X squared. And let's just kind of fill that out right now with what we know it to be, because we already listed the cast of characters. K is 85, and x squared, I should really put that too. The x in this case is 0.035, so let me make sure I have enough room to write that. 0.035. All right, I'll just save room by doing that. And at that point, you are indeed ready to simply plug that into your calculator, and you would get, as a result, 0.052. Now that's going to be joules, because once again, that's energy, okay? So that is that one. Looking at lowercase letter c, how does the total energy of the block spring system change as the block is pushed across the frictionless surface? Well, the total energy of the entire system doesn't change, okay? And that has to do with the fact that the original energy will equal the final energy no matter what. So, and there's no work being applied from the outside of the system, so it's a closed system. So the energy actually does not change. And when I say the energy does not change, I mean the total energy does not change. And that's what they're asking about, right? They're asking for about the total energy. So we could literally say, okay, total, I'll just call it TE. Okay, I don't feel like writing that. Doesn't change. And I would just say because the system is closed. Because closed system. Okay? There's no work being applied from the outside. And one of the laws of physics is that when you have a closed system, the energy does not change. you can think of the fact that energy cannot be created nor destroyed. That's a related concept. So the maximum velocity of the block, well, once again, anytime they're talking about how fast, you should start thinking about kinetic energy. Now, I will say it's also the case up here. We have some sort of interesting relationships where gravitational potential energy equals kinetic energy. Um, that this is another way of saying the same thing, actually. And we could also recognize that, oh, v squared equals 2gh. That's all related. Let's ignore that. Okay, this is the one that we want. So elastic potential energy also equals kinetic energy. So notice how like potential energy equals kinetic energy, right? That's a theme that's happening here, right? Potential energy equals kinetic energy. Potential energy equals kinetic energy. Doesn't matter if you're dealing with gravity or elasticity, springs or whatever, potential energy equals kinetic energy. So that is hugely helpful because we already found the elastic potential energy. It's this, right? So we can set that equal to the kinetic energy expression. Now the kinetic energy expression is featured once again right here. There it is. And in a way, we've kind of already done this, we've already done a problem exactly like this. So what I'm going to write here soon, before I zoom in, is, 1/2 the mass times v squared. And I'm going to set that equal to, what is it, 0.052, right? 0.052. And once again, that's because the elastic potential energy equals the kinetic energy, and the kinetic energy is this. So we are going to do that. I'm going to go off to the side over here. I think once again, we'll treat it like a literal equation, once again, like we did with the last one. And what I mean by that is we will have our 0.052 joules, but that equals 1/2 mass times velocity squared, okay? So 1/2 mass times velocity squared, that's right here, that's the kinetic energy. So to find out V, we would have to move everything around, and we would end up with 2 times 0.052 all over the mass, and it would be the square root of that whole thing. That's going to equal the actual velocity. All right, so once again, had we done everything we could to get v by itself on the right, we would end up with this on the left, okay? Now, we know what the mass is. The mass is given. It is 0.8, so we're going to simply put that in here, right? 0.8. And at this point, we can just plug this whole thing into the calculator. And that would give us approximately 0.36, and that's meters per second. So notice how it's really just a matter of being loosely familiar with what's on here, maybe even using this section right here as a guide with regards to where you should be focusing on. If there's height mentioned, you might want to look at this: gravitational potential energy, kinetic energy, how fast, anything that has to do with springs or compression or stretching, that's the EPE, elastic potential energy. So that's good to know. All this stuff is good to know. Nice little resource. And the answer is 0.36 meters per second. So let's put that here, 0.36 meters per second. Okay, so that concludes this first page. Now, obviously, there's this problem here, but I'm going to move to another slide, a slide that features that problem. Hopefully, that makes sense with regards to the first page. Okay, so here is the second page. And looking at the first problem. A small block with a mass of 1.5 kilograms starts from rest at the top of the apparatus. Now they're saying shown above, but it's really this. Okay, so that's a formatting issue. It then slides without friction down the incline around the loop and then onto the final level section on the right. It then collides with a spring, which momentarily brings the block to a stop. The maximum height of the incline is 2.5, and the spring constant is 90. Well, this problem sort of merges some of the stuff that we've done before. It's a very similar diagram. You have a block up here, it slides down, it's going to do a loop, and then it's going to go this way, it's going to hit the spring, and it's going to come to a stop at some point. And similar to the first problem, I think it would be helpful to get clear about the height, which is 2.5 meters. Now, meters does indeed happen to be the unit of measurement we want, so we do not have to do any unit conversion. They also tell us the mass of the block, which is 1.5 kilograms, and I am happy to say we don't have to do any unit conversion there either, because kilograms is what we want to work with when we're trying to figure out or trying to work with mass in general. So the K constant, the spring constant, this K is 90, so we're just going to say that is 90 newtons per meter. So yeah, we sort of properly labeled everything. I think that's all we can say at this point. Is there mention of the radius? I don't think there's any mention of the radius, and that's okay. So we're going to keep going. Okay, find the initial potential energy of the block. Well, the block is up here, which means there's a height involved, which makes me think, okay, well, we're probably going to be dealing with gravitational potential energy. And that is something that we've actually already done. You know, I think problem number 1 featured the exact same situation. So gravitational potential energy is going to be mass times the gravity times the height. So that's going to be really straightforward, really straightforward. So I'll just write that. GPE equals mass times gravity times the height. Again, we don't need any unit conversions. We can just plug all the numbers right in. So the mass happens to be 1.5, 9.8 for gravity, and the height is 2.5. And when we use a calculator to multiply all that, we get 36.75, and that would be joules. So once again, I do believe the teacher probably would appreciate, at least at the very end, to have the unit of measurement in the final answer. Okay, looking at lowercase letter b, find the velocity of the block at the bottom of the loop. So velocity, you know, once again, we should be thinking, if it's how fast, we're probably going to have to deal with kinetic energy, and kinetic energy is right here. That's 1/2 mass times velocity squared. So we could always take this 36.75 and put it here and then set it equal to 1/2 mass times velocity squared. Now, that would totally work. However, I'm going to try a different approach this time, because up here we do have some ways of making our lives easier. So for example, right here it literally says gravitational potential energy equals kinetic energy. I mean, ultimately that's really what we're dealing with, right? And we already found the GPE, it's this, so we already know what the GPE is, and we want to know the velocity. So we could take advantage of the fact that GPE equals KE, gravitational potential energy equals kinetic energy. And what this is showing is that, okay, gravitational potential energy is mass times gravity times height. Kinetic energy is 1/2 times mass times v squared. So you could actually mess with this equation, cancel out the m's, and then you end up with a situation where it's v squared equals 2 times g times h. And I would even take that further, actually. I would take that further and say that v therefore equals the square root of 2 times g times h, okay? Now, that's another way of going about it. In a way, this is kind of a shortcut. It's kind of a shortcut. So I'm going to say let's use the shortcut. Now, once again, if you wanted, you could set the GPE equal to 1/2 mass times velocity squared and, solve for velocity. But we're going to use a shortcut. We know that V equals square root of 2 times g times h. So let's do it. So I'm going to write that here. V, velocity, equals the square root of 2 times gravity times the height. And we know that 2 is 2, the gravity is 9.8, and the height was 2.5. And when you plug that into your calculator, don't forget to do the square root of the whole thing, right? That's going to become 7, and that would be meters per second. That's the unit of measurement for velocity that we like to work with. So that is the answer to that one, looking at lowercase letter c. How much will the block compress the spring before momentarily coming to a stop? So the word compress. Here's the word compress. That means we want to deal with elastic potential energy. Elastic potential energy is over here. Awesome. So let's see, we have 1/2 K, that would be the constant which we have, that's 90, and we have the displacement squared. Well, the displacement refers to how, what distance the spring is compressing in, okay? And that's ultimately what they're asking us. When they say, how much will the block compress the spring, that means, what distance will be covered in the compression of that spring. So that's a length question, if you think about it, okay? If I want to know how much, let's say I have a spring here, right? And then I compress it so it looks like, let's actually do it over it. Let's say I start with the spring there, but then I compress it so it looks like this. Well, didn't I just compress it a certain length, right? That's the, so if you ask, how much did you compress the spring? It's basically saying, like, how much distance did you compress it over? Okay, for lack of a better way of putting it, okay? So how much means how much ground did you cover during that compression? So that might be a way of seeing it. Now, let's answer this by acknowledging something. And here's what we're going to acknowledge. According to this wonderful resource up here, we can see that gravitational potential energy equals kinetic energy. We also see that kinetic energy equals elastic potential energy. I feel like that's enough information for us to also realize that gravitational potential energy equals elastic potential energy. Okay? So, yeah, I mean, by law of substitution or maybe even transitive property, if this equals that and that equals that, then this equals that. Okay? So that is true. Okay? And that's the insight that we're going to need here. Okay? That's the insight we're going to need. And let's take a look at it. Let's see, how much will the block compress? Well, keep in mind, we already have the GPE, it's this, and we know that the GPE equals the EPE. The EPE is the one that has the X in it, right, and the spring constant. So we can really just crush this problem by recognizing, okay, GPE equals the EPE. We already have the GPE, it's from here, that's 36.75. So 36.75 equals, well, what is the EPE? The EPE is 1/2 K times X squared. 1/2 K times X squared. Now, we are keeping in mind that it's really this X that we're trying to solve for. And, you know, we could sort of begin the process of filling in our K uh, and all that stuff, but, I'm actually going to go ahead and treat this as a literal equation as well, where I'm going to get x by itself. Now, if we were to go through the motions to get x by itself, we'd quickly see that we would have 2 times 36.75. I mean, it'd be the square root of the whole thing over k, okay? So in case that's not clear, you could get x by itself sort of on your own, pause the video if need be, and it would be this. Now, again, I like doing this because then I could just do one single calculation in the calculator. So with regards to that k, we already know that this k is 90, okay? That was given in the problem, so I'm going to replace k with a 90, and then we will go ahead and just find out what this is in the calculator, and it is approximately 0.9, and that would be meters, so approximately 0.9 meters. So I'll put the x over here. Okay. Let me rewrite this. 0.9 meters. So yeah, that's how you do that one. What is the moral of the story there? The moral of the story there is that GPE also equals EPE. Gravitational potential energy, we could see that as equaling elastic potential energy due to the closed system aspect of this mechanical system here. And therefore, whatever you find with regards to gravitational potential energy, such as 36.75 joules, we already knew that, you can set equal to elastic potential energy, and elastic potential energy features 1/2 k times x squared. X represents the displacement, and we could understand that the displacement is how much the block compresses the spring. How much the block compresses the spring. So hopefully that makes sense. Moving on to the next one. Okay, so let's find out what we have in store for us here. A roller coaster, so once again, the formatting is kind of weird, but this is a roller coaster of mass 500 kilograms. Starts its ride from rest at point A. Okay, so the format is already driving me crazy. I'm just going to start labeling stuff. 500 kilograms, great. The height is 70 meters. Great. No mention of what this radius is, and that's okay. Ignore friction force. Okay, so we have kilograms, which is the unit of measure that we want, and we have meters, which is the unit of measurement that we want. Now, in case my student at home has not recognized, hopefully you recognize that, number one, you're definitely going to want to label the diagram. I mean, no question. But you know what? I would actually say, too, that when you're labeling it, make sure you're already dealing with the unit of measurement that you want. So if this was like, 50 grams or something, I would, maybe I'd write 50 grams here, but I would immediately off to the side do a unit conversion, and then I would write equals, what would that be? 50 grams would be 0.05 kilograms, pretty sure, 0.05, okay? So label the diagram, but also do the unit conversions right away, and then, properly label the diagram, okay? So cool. Looking at the first one, how much work is required to bring the car to point A? So you start from the ground, and it requires work to go up there. Now that's the first time we've been asked about work, and the good news is there is mention of work. Here we have that work is equal to force times displacement, but we could also say, according to this information here, that work is equal to, at least as it pertains to the work required to lift something, work is equal to mass times gravity times height, okay? And for the record, it's also the case that gravitational potential energy also equals the work. Okay, so the moral of the story here is that if you're lifting something, it's going to take work to lift it. Okay, if you're lifting something, it's going to take work to lift it. So it's better to use this equation when analyzing those circumstances than something like this, because this is a little bit more specific to the fact that we're uh, analyzing height and gravity and so on. Okay, now there is a way to get from here to there, but I don't really want to talk about that. Okay, the teacher probably explained how this is really, you know, ultimately it's saying the same thing. But just know that if you're going to be lifting something, then, and the question is asking you about work, you're going to want to pay attention to this. So work equals mass times gravity times height. So that's going to be really straightforward, actually, isn't it? The work is going to be mass times gravity times height. And all of that is stuff that we have. Now, the mass is 500, gravity is 9.8, and the height is 70. So another super straightforward problem. So when you multiply all that across, that's going to become 343,000, and that is energy, so that's joules. Well, it's work. Work is in joules as well. Okay. Okay, so calculate the velocity of the car at point C. So velocity, once again, I think my student at home, I'm sure my student at home is getting it now, that when there's mention of velocity, we should be thinking about kinetic energy. And also, you know, it's kind of cool to see that, let's check this out. I think everyone's going to appreciate this. We want to figure out the velocity, right? We want to figure out the velocity of this thing. It's like going down and then it hits a velocity right here. It's sort of at its maximum velocity at this point. And since there's no friction, it's sort of maintaining the velocity as it goes over there. So we want to find the velocity right here, right before it goes up, you know? And the velocity is going to be relatively high at that point. And let's be very clear about the fact that it was on the last slide. So I'm going to rewrite the fact that V equals radical 2GH. And it's really all we need. It's really all we need. Okay. Now, again, we could be focusing on kinetic energy equals 1/2 mass times V squared. The kinetic energy does equal the gravitational potential energy. The gravitational potential energy equals the work. And we already have the work. It's 343,000, right? So we could say that, you know, the work, 343,000 equals kinetic energy and do this whole thing, or we could just simply use this thing, right? So velocity equals the square root of 2 times g times h. Crazy. I think I'm going to go with that one. I think I'm going to spare myself any confusion and just use that one. Now, my student at home, you might be wondering, is it okay if I just use that? And my answer to you is yes, use it. And you know how I know this is okay for you to use? Because there was a moment in the teacher's notes I did see on a slide, there was a moment where the teacher mentioned this. And in my opinion, this thing is just a short step away from this, which is something your teacher did give you. Okay? So teacher gave you this in the slide, probably as a way of saying, hey, here's a shortcut in case you want to use it. And I'm saying, let's make it even more shortcutty by taking the square root of both sides. This is literally a way of figuring out the velocity when it comes to these kinds of problems. So we're going to have 2 times gravity, which is 9.8, times the height, which we already know is 70, right? Let's make sure that's extended. Sometimes teachers like to do that just to make sure it's clear that the 70 is included. So if I was to plug that entire thing in to the calculator, including the fact that I'm taking the square root of it, it would be approximately 37.04, and that's velocity, so it's meters per second. Okay, looking at this one, on the figure of the car below, draw and label the vectors to represent the forces acting on the car at point C. So we're imagining this car is right here. Now, what's happening? First of all, we know we have a vector of gravity, or weight, going down, I should say. Weight. Now, weight, just so you know, is mass times gravity. So that's something that's definitely acting on the car, really at all times, okay? At all times. Now, let's say you were in the car, or it's a roller coaster, right? But we'll just call it a car, I guess, because they're calling it a car, right? A roller coaster car. In this moment, if you've ever taken a roller coaster, you're going to feel really heavy in this moment as it's like right about to lift off right there. And that heaviness means that the seat is pushing up against you. That's what feeling heavy means. It means the seat feels like it's pressing up against you, okay? Or the floor feels like it's pressing up against you. Now, the reason it feels like it's pressing up against you, interestingly enough, is because it is. It is pressing up against you because there's an equal and opposite reaction going on there with something called the normal force, okay? So we have the weight pushing the car down or acting on the car and bringing it down, and then we have that counteracting normal force pressing back up. Okay, so that's the answer to that one. With regards to this one, on the figure of the car below, draw and label vectors to represent the forces acting on the car as it is upside down on point B. So that would be right here. So if you've ever taken a roller coaster, you're going to feel really heavy right here, and then you go up, 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 and then there's a moment where you feel weightless, and then you go in this way, and then you're heavy again, and you're like that. Okay? So this moment, you feel weightless. Now, what does feeling weightless mean? What does that mean? That means your butt is lifting off the seat, kind of, in this moment, right? So let's be very clear. There's still a vector of weight happening here because that's always happening. It's always going down. This mg thing, mass times gravity thing, that's always happening down. But when you're upside down, the normal vector is also going down. Okay? Now you could think of the feeling of heaviness as being the result of these vectors being in opposition to each other. I think that's one way of thinking about it. When weight is in opposition to the normal force, that's when you feel heaviness. That's when you feel that pressing action, because there's like a conflict going on here. But when your weight and the normal force are not in opposition to each other, that's when you have the experience of weightlessness, even only for a moment. Okay, so when these are not in opposition with each other, your butt's not pressing hard against the seat, and there's a feeling of weightlessness. When they are in opposition with each other, your butt is pressing hard against the seat, and therefore you feel heavy in that moment. Okay. Okay, now suppose that friction is not negligible. How would friction affect the answer to B? Well, there's a lot we could say about friction, but let's be really clear. B asks, well, what would the velocity be at point C? Well, the friction of the floor would have slowed the velocity down by the time he got to C. Okay, so that's pretty intuitive, I would say. You're going down, 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 but then you hit all this friction, so you know what? You're going fast, but you're going to slow down by the time you get to C. So the friction would slow the velocity. maybe we could say the friction would decrease the velocity. It would decrease the velocity. All right, I think that's all we need to say there. There's no mention of, any other information with regards to friction, so I think we just keep it very general. All right, problem number 5. Student uses a spring-loaded launcher to launch a marble vertically in the air. The mass of the marble is this amount of kilograms, and the spring constant is 220 newtons per meter. What is the maximum height the marble can reach when compressed 2 centimeters? Well, it looks like that's actually a question, right? That's the first question. So maybe if we drew a picture, we could sort of get an idea of what's happening. Let's say that the spring is compressed 2 centimeters. Now, I'm going to get clear that that is a certain amount of meters, also known as, so it'd be 1, 2, right? Yeah, so it would be 0.02 meters. We're going to want that distance in meters because that's the proper unit of measurement there. So even though they said 2 centimeters, we're going to want to write 0.02 meters, okay? And that's how much the spring was compressed. So it was here, but then it went down. And there's a marble that's going to be, launched eventually up. So we're going to put the marble here, but we could also imagine once it launched up, it reaches a certain height, right? Now, we'll assume, the height has to do with, where it took off from. Let's imagine where it took off from was the floor. I know it doesn't look like it, but imagine when you compress the spring, it goes all the way down to the floor and then it shoots up. Okay, so let's just imagine that, just to keep it simple, because I'm sure that that's sort of what they mean. So we want to know the maximum height. So that is the question. We have a constant K right there. So we'll keep that in mind, maybe next to the spring, 220. Okay, so this has to do with height, and once again, if we're dealing with height, well, GPE might be good. GPE might be good. Now, one of the things that I had mentioned in the last thing is that GPE, since it equals kinetic energy, GPE also equals elastic potential energy. So this could be the ticket, seeing as how this has to do with a spring and this has to do with height. Setting these two equal to each other and working with those could be the ticket to finding the answer here. I'm going to say that it probably will be. So let me just go ahead and write GPE equals EPE. So I'll write that over here. GPE equals EPE. Now we could be clear that GPE is equal to the mass times gravity times the height, right? Mass times gravity times the height. So I'll write that here. Mass times gravity times height. And that equals EPE. Now apparently EPE is equal to 1/2 K times x squared. Okay? 1/2 K times x squared. And what do we have? Well, we have our x, which is the displacement when you compress the spring. That's 0.02 meters. We have the spring constant, K, which is 220. We don't have the height. We want to find the height. Do we have the mass? Yes, we have the mass. That's 0.003. And we have gravity. So it looks like we actually have everything we need to solve this. Now, I'm going to draw my student and really everybody's attention to the fact that we are solving for height in this problem. So I'm actually going to go ahead and rearrange the formula now so that it's H equals 1 half kx squared all over m times g. Okay, now how did I do that? Well, I wanted to get this h by itself, so I just divided everything by this m times g, this mg, and it ends up on the bottom. So if you're not feeling very clear about what I did there, you could always pause the video and just try it yourself. Just get h by itself, divide both sides by mg. And again, the reason I'm doing it that way is because I want to really only do one calculation in my calculator if I have to. So I have 1 half times k. The constant is 220. We already knew that. X squared. Well, the x we already discovered. The compression displacement we already discussed is 0.02, right? So we're going to put that in there. That's 0.02. Blow it up a little bit more. 0.02, and that's all over the mass times gravity. Well, I'll do two parentheses here. We already know gravity, it's 9.8. And the mass they gave us, it is 0.003 kilograms, right? 0.003. So we'll make sure that's there, 0.003. Okay, now again, it's a little bit crazy looking, right? But we're about to find h. H equals this. Okay, so all we have to do is plug that into the calculator. Be very careful with it, and we're going to have our h soon. So h is 1.5 meters approximately. So that's the maximum height. That would answer the first part, which is kind of weird because this question doesn't have a letter, and then they get into the letters, but that was a question. So I feel like we should answer it. Okay, well, now there's a lowercase letter a, which I find to be interesting because really this looks unrelated to the one that we just did. So, but we're going to go with it. So what happens to the kinetic energy of an object if its velocity remains constant and the mass triples? So really what they're saying is investigate the kinetic energy equation, and that is over here. Now, according to this, kinetic energy is 1 half times mass times velocity squared. So I'm going to write that. Kinetic energy is 1 half mass times velocity squared. So they're painting a picture where the velocity remains constant, so the v remains as is, but the mass triples. So they're like, ooh, what happens to the kinetic energy? Well, I'm going to write over here a big question mark. I'm going to be like, okay, I don't know. What happens? What happens when we have 1 half and then we multiply that mass times 3 and the velocity stays the same, right? So this is all the same stuff as here, except we sort of interjected a 3 in there. And that 3 is being multiplied to the mass because that's what they're asking. Right? They're like, the mass triples. Okay, here's us tripling the mass. Great. Well, this could be rearranged so that, I mean, if you wanted to, it could be rearranged so that the 3 is kind of on the outside, because this is just a string of numbers being multiplied together, and multiplication is commutative, which means I could take this 3 and bring it over here. So the 3 is over here, and it's still the same thing as this. Okay, it's just I'm moving things around a bit. Now, isn't this 3 times the original kinetic energy function? I mean, the original kinetic energy equation, I should say. Well, actually, it is a function now that I think about it. But the original kinetic energy equation says, oh, kinetic energy equals 1 half mass times velocity squared. Well, that's right here, right? So that is, 3 times kinetic energy, right? Because 1 half mass times v squared, well, that is kinetic energy, and it's 3 times that, so it's going to be 3 times kinetic energy. So that's one way of seeing it. Now, do you have to write it exactly this way and do all this stuff where you shuffle things around? No, not necessarily. I mean, it's possible that, at a certain level of experience, you just see, okay, let me multiply the mass times 3. Oh, I can see what's going to happen here. It just triples the whole thing because the 3 could be moved to the left, okay? So how would you answer that? Well, you would say the KE triples. That's a very quick way of saying it. Okay. What happens to the kinetic energy of an object if the mass remains constant and the velocity triples? Okay, well, that one's a little bit trickier because, once again, here's the original thing. And we're imagining a situation where the mass stays the same, but the velocity is tripling. So, once again, we can kind of do it in a similar format where it's 1/2 mass. But now it's going to be 3 times v, and that's squared. Notice how the 3 is going inside the parentheses because it's now 3 times the old velocity, the new velocity, we could say. This is the new velocity, which is 3 times the old velocity. So that new velocity needs to get squared. Hopefully that makes sense. And as a result, that would become 1/2 times m times 9 v squared, because that exponent of 2 gets applied to the v and the 3. If the 3 is inside the parentheses, that means the exponent of 2 would get applied to that 3. So we have this situation. Once again, since multiplication is commutative, we could kind of put that 9 out front. So it becomes 9 times 1/2 m times v squared. And that is equal to 9 times KE, right? Because this is KE. So we could say the kinetic energy I don't know, what's the word for multiplying by 9? Let's just say gets multiplied. It's probably a very clunky way of saying it. It gets multiplied by 9. Okay. I'm happy with that. What happens to kinetic energy of an object if the velocity doubles and its mass is a quarter of its original mass? All right, now they're just getting crazy. What's going on over here? Once again, let's write the original thing. Okay. And now we want to know, okay, what's going on when the velocity doubles? So I'm going to write that over here. 2v. We still have the 1/2. The mass is a quarter of its original mass. So the mass is 1/4 of what it used to be. So I'm actually going to write 1/4 times the mass, because if the mass is a quarter of what it used to be, well, that's the same as multiplying the original mass by 1/4. Okay. And then we're going to have to work that out, right? So let's see. We're going to have a 1. Let's bring that 1/4 out actually first. So we're going to have 1/4 out front. And we still have the 1/2 here. We'll worry about simplifying it later. Now, as a result of this, remember that exponent of 2 gets applied to the 2, and the exponent of 2 gets applied to the v. So that would become 4v squared. And then I would put all this sort of new stuff out front. I'll keep it in black. So it's going to be 1/4 times 4 times 1/2 mv squared. Now, I think my student at home is probably getting this because, as I said over here, well, KE equals 1/2 mv squared. So this 1/2 mv squared equals KE. So that's cool. Let me just write that. It's kind of a a few different ways we could go with this, but I'm just going to get this over with and just write that. All right, KE. And I'll color code the green brackets there. So what happens? Well, this happens. Right? This happens. But what is this? What is 4 times 1/4? 4 times 1/4 is just 1. Right? It's just 1. So you know what we get at the end of all that? At the end of all that, we are left with KE. So when they ask what happens to KE if the velocity doubles and its mass is a quarter of what it used to be, what happens? Nothing. Okay? The KE remains the same. Okay? So I'm being a wise guy by writing nothing. But if you want to be a little bit nicer, you could say it remains the same. Okay? So anyway, that is how you do everything on this review sheet. I hope it made sense. So for my student at home, pause it, rewind it, whatever you got to do. I think one thing is for sure, you must copy this. Must copy this. Okay. And I would even add the following. I would make sure that it's also clear that GPE equals EPE, and I would also make it clear that because of this, it's true that velocity would equal the square root of 2 times g times h. Okay? That is something that really came in handy a couple times on this review sheet. It allowed you to bypass a lot of work. There are other ways of finding out the velocity, by working with the kinetic energy formula and so on. But if you have the height of something and they're asking you about the velocity once it gets down to the bottom, you might want to just use that. Okay? So that hopefully is helpful. I will talk to you all later. If I made any careless mistakes, which I do not think I did, but if I did, please let me know in the comments. I do make mistakes every now and then. I can guarantee you that the process by which I solved all of these problems is sound, and I encourage you to use the steps that I did. So good luck to my student and good luck to you folks at home, and I will talk to you next time. Bye.